Hello. Today we will continue from what we had yesterday on 5.1. Yesterday we pretty much stopped at the conversion between radian and degree, where pi radian is equal to 360 degrees. Now, sometimes we don't write the radian, we just write it as pi. Consequently, I'm sorry, not 360, 180. Consequently, then the special angles, 30 degrees is pi over 6, 45 degrees is pi over 4, and 60 degrees is pi over 3. Now we will go on further. Actually, we did yesterday. We go on further that 90 degrees equivalent to pi over 2, and of course 0 degree is simply 0 radian. Now in general, when we convert from degree to radian, we multiply by pi over 180 degrees. Suppose for example, if I have 75 degrees, I need to cancel the degrees and change it to radian. So I use the proportion or the ratio we have up here. Okay, I use that ratio. That's pi over 180 degrees. That way the degrees will cancel. And we get 75 over 180 reduced by 15. If I reduce by 15, that would be 5 pi over 12. That's in radian. Again, sometimes we don't write that radian unit because radian measure is actually a unitless measure. Okay. Now, on the other hand, if we want to convert from radian to degree, then we will multiply by the reciprocal, multiply by 180 degrees over pi. So for example, if we have 3 over 5 pi radian, so 3 pi over 5 times 180 degrees over pi. Yeah, we know that it is in radian if it doesn't use degree sign, and they say that's a measure for angle. Then you see the pi cancels. In this case, actually I can cancel the 180 with 5 also. Reduced by 5, that's 36. So that's equals to 108 degrees. Okay, that's the conversion from degree to radian and radian to degree. It will be nice if you can memorize the special angles. Try to memorize, I write it down here in red. Try to memorize special angles between 0 degrees to 90 degrees in degrees and in radian. In degrees and radian unit. Okay, I need that. I need that. In fact, we will see that very soon. We will see that very soon. Okay, now, what is the use of radian? What is the use of radian? Use of radian. By the way, when you go to calculus, most calculus computation angles, I think I should say most angles in calculus. Most angles in calculus is given in radian, or the work is done in radian. Okay, now, but the one that we can use right now, the uses of radians, first one, arc length. Suppose we have an arc that is part of a circle. So we have known yesterday that if this is the center, this is the radius, the angle theta in radian here is the ratio between the arc length, and the radius. If this is S, okay, theta in radian equals to S over R. Okay, now consequently, if we want to find the arc length, that's equals to the theta times R. Okay, now the thing is the theta needs to be in radian. Theta needs to be in radian to use this formula. Okay, that's for the arc length. Now, the second use is on sector area. Now, sector area here is this region, the area of this region. That's the area of that region. Okay, while the arc length refers to the arc. Now, how about the sector area? Now, the sector area of sector, let me draw it like a pizza, that's equals to 1/2 theta r squared. That's the formula. Now the proof. Now notice that the sector area is proportional to central angle. So the larger the area, the larger the angle. Okay, now then we learned this proportion word before, right? So basically that the area of the sector equals to a constant multiple of that theta. Okay, now the thing is, what is that constant multiple of theta. It turns out that we can do it in the following way, that we know that the area of a circle is equal to pi r squared. Right? The area of the circle is pi r squared. So the area of the sector divided by the area of the full circle is equals to the central angle of that sector over the area of the full circle. Actually, I'm sorry. No, that's not this. The angle, central angle of the full circle is 2 pi. So this is the sector. This is the full circle. That's for the area on the top. I mean, the left-hand side is the area, the right-hand side is the angle. Now, but we also know the area of a circle is pi r squared. So the area of the sector over pi r squared equals to theta over 2 pi, such that the area of the sector is given by theta over 2 pi times pi r squared. Now you see the pi cancels, such that the area of the sector is 1/2 theta r squared, as we expect it to be. Okay, so this is the arc length and the sector area. Examples. Suppose we let theta be 120 degrees and the radius is, let's say, 10 centimeters. And so imagine if you have a circle, let me make it a bit bigger, and then the central angle is 120 degrees. And the radius is 10. And the first question is, what is the length of the arc? What is the length of the arc? So part A, what is the arc length? And part B, what is the area of the sector? Okay, actually, the third one I can ask, what is the perimeter of the sector? Okay, but before I actually start any one of them, I need to convert that theta first. So let me do solution. I need to convert that theta, which is in degrees, first into radian. So multiply by pi over 180 degrees, reduced by 60, that's 2 pi over 3. So part A, the arc length S is theta r, which is in radian, 2 pi over 3 times 10, that's 20 pi over 3 centimeters. Then from there, if you want to approximate that, go ahead, 20 pi over 3 give me 20.94395 centimeters. 5 decimal places. Okay, now how about part B, the sector area? Area of the sector, that's 1/2 theta r squared. That's 1/2 times 2 pi over 3 times 10 squared. That will be 100 pi over 3 and then 100 4.71976 centimeter squared. Okay. Oh, by the way, before I go on with part C, by the way, we see that the area of the sector is equals to 1/2 times theta r times r, right? And theta r turns out to be the arc length, right? So this is now equals to 1/2 s r. Yeah, if you happen to know the arc length and the radius, you can find the area of the sector directly. Okay, so the alternative way to do part B, since we already have the arc length, right? So the area of the sector is equals to 1/2 times 20 pi over 3 times 10. Okay, 20 pi, not 20 pi, 20 pi over 3. That's how we get that 100 pi over 3 centimeter cube, centimeter squared. Now, part C makes you think a little bit. How about the perimeter of the sector? Now, if you take a look on that sector, the perimeter is the blue shades plus twice the radius. Plus twice the radius. You see that? Okay, so to enclose this region here, this segment, and this sector, to enclose this sector, okay, I need the arc plus twice the radius, right? I need the arc plus the radius, twice the radius. So then the perimeter of this sector will be twice the radius plus the arc length. Okay, 2 times 10 plus 20 pi over 3. Okay, that's 20 plus 20 pi over 3 centimeter. That will be 40.94395 centimeter. Now that's for arc length and sector area. The other two uses, part 3, is linear speed. Yeah, linear speed, just like the one we learned before, rate equals to distance divided by time, right? But in this circle, the distance becomes the arc length divided by time. Okay. Now, this rate that we usually use R to represent that speed, we then can, actually our textbook use R also. Now, that's linear speed. So basically, if you have a circle, and this is theta here, okay? So the linear speed is the distance you travel over a period of time, and the distance here refers to the length around the circle that you travel. Okay, but we know from the first part that the arc length is theta times r, the radius. Now I have two r's. Then I hope you realize that we don't want to use that r. We will use the linear speed. Let me erase that. R becomes phi for velocity. Phi for velocity or linear rate, linear speed. That's the linear speed, while angular speed is the angle traveled over a period of time, and it is denoted by omega. That's the angle traveled over a period of time. Okay, now compacting these two formulas, then you see that the linear speed is actually equals to the angular speed times the radius. Okay. Now your suggested homework from here, actually, let me do some problem from this linear speed and angular speed. Suppose I look at number, what is the number in our textbook, number 44. Number 44. A simple model of the core of tornado is a right circular cylinder that rotates about its axis. So let's say this is our tornado. Okay, and it's a right circular core. It's a right circular. I'm sorry, that's right circular cylinder. It's a cylinder. That rotate around its core. So let's say this is the core. Okay, now if the tornado has a core diameter of 200 feet, so the diameter is 200 feet, and maximum speed of 180 miles per hour, so that's the linear speed, right? The velocity is 180 miles per hour, which is equivalent to 264 feet per second. At the perimeter of the core. So the speed at the perimeter of the core, the speed here at the perimeter of the core is 264. Now the diameter is 200. The diameter is 200 feet, so the radius will be 100. Okay, now approximate the number of revolutions the core makes every minute. So the question is, the find number of revolution per minute. So how many times you encircle the axis if you have that speed? Number of revolution per minute. So this is basically the omega. Okay, that's basically the omega. Now, let's see. We know that the linear speed is equal to theta times radius, right? The linear speed is 264 feet per second. No, not omega times r. Not omega times r. I said it right, but I wrote it wrong. It's omega times r. So I actually wrote it wrong. Yeah, I wrote it wrong here. I wrote it incorrectly here. It's supposed to be omega. Good thing I realized that. The omega is linear, the angular speed. The omega is the one in question. The radius is 100 feet, right? Okay, so when I divide 264 feet per second divided by 100 feet, that will give us the omega, which is 2.64 per second. Now you see that we don't have units there, okay, because the feet cancels. Now that becomes radian per second. That becomes 2.64 radian per second. Now per minute, it will then be, the omega will be 2.64 times 60 radian per minute, because 1 minute is 60 seconds, right? 2.64 times 60, that's 158.4 radian per minute. But what we need is not radian per minute. What we need is revolution per minute. Now, one revolution is one revolution. The angle is 2 pi radian. So the omega in revolution per minute will be 158.4 over 2 pi revolution per minute. Now that RPM stands for revolutions per minute divided by 2 pi. That will be 25.21014 RPM. That's the number of revolutions per minute. So imagine if you are actually at the point of that, at the perimeter of the tornado, and you are being flown. Then in 1 minute you flew around the axis of the tornado 25.2 times approximately. Okay, that's for number 44. Number 48. Number 48. Given the radius is 9 inches and the omega is 2,400 RPM. Again, RPM is not radian per minute. RPM stands for revolution per minute. Maybe I write it down in red. RPM is revolutions per minute. Okay, so in part A, find the angular speed. We actually already have it, they're given to us, the angular speed, but the key is in radian per minute, radians per minute. Okay, so omega, which is 2,400 revolutions per minute. One revolution is 2 pi radian times 2 pi radian per minute. That would be 4,800 pi radian per minute. Okay, and then part B, find the linear speed. Find the linear speed in feet per minute. In feet per minute. Now the linear speed velocity equals to omega times r. Right, so that's 4,800 pi times 9 inches per minute. Now the thing is, we actually want that in feet. So 4,800 pi times 9, that's inch per minute. Now we convert that to be feet per 12 inches, right? Because 1 foot is 12 inches. That way the inch cancel. Okay, so we get, this will be 48 divided by 12, that's 400, 3,600 pi feet per minute. Okay, so in 1 minute, whatever this thing is, a wheel actually travel as far as 3,600 pi feet per minute. In 1 minute, it travels more than 1 mile. By the way, 1 mile is 5,280 feet. Question mark. Is it 5,200 or 5,100? I think it's 5,200. Yeah, I think it's 5,280 feet. Okay, now this 3,600 pi feet is definitely more than 5,200. Let's compute that. That's the exact solution though. But if I want to find the approximate solution, that will be 11,300. Actually, it's more than 2 miles. Huh? 309.73355 feet per minute. Okay. By the way, you see a lot of that RPM notation actually in your car, on your car. In fact, the car, when you drive a car, the units is actually in 1,000 RPM. The unit is in 1,000 RPM. Okay, now that's for number 48. Should I do number 50? Do I want to? You can just do it yourself. Okay, go back to 5.2. Go back to 5.2. Not really 5.2 though, but let me finish. Say that this is the finishing up of 5.1. This is 5.1b. Now then in 5.2, in addition to what we learned yesterday, yesterday was the foundation. Yesterday was the foundation. Now yesterday we learned that we define the trig functions on a right triangle as, this is yesterday. If this is A, B, C, where this is vertex A, this is vertex B, this is vertex C, then we say sine A is equals to A over C, cosine A is B over C, and tangent A is A over B. Now that's yesterday. That's the very, I like that, I like to start from there because in my, according to what I saw, we can understand trigonometry at early stage by looking at the right triangle. But there's a weakness of this right triangle approach. One weakness of right triangle approach is it can accommodate an obtuse angle, any obtuse angle. In fact, it can accommodate any angle outside of 0 degrees to 90 degrees. Okay, I write it in interval notation. So we will find another method. So we will try to extend the definition of the trig function, the trig functions. How will we do that? How will we do that? We'll do it in the following way. We will start from rectangular coordinate system. No, this is not way. I start from rectangular coordinate system. Okay, and let P be a point on that rectangular coordinate system. Let's say this is point P, x, comma, y. Let P with coordinate x, y be a point on the coordinate system. I think I should say the coordinate system. And theta is the angle associated to that point. So what I'm trying to say is you have an angle theta associated to that P. Okay, this is the theta. And I didn't tell you the angle, therefore it must be in from where, then it must be in standard position. Okay, the theta is in standard position. Okay, now notice that right now my theta is still an obtuse angle, so I can do it this way. This is coordinate, the x, and this is the y. Let's call this the r. Okay, where the r equals to the hypotenuse of that right triangle. Now then we can define, sine of that theta equals to y over r. Notice that sine of that theta, imagine this triangle here. Imagine this right triangle here. Now, the opposite of the theta is y. The adjacent of theta is x. Right? Okay, so as if now you are looking at this triangle. This is theta, this is y, this is r, this is x, this is r. So using our right triangle point of view that we have yesterday, then sine theta is y over r, cosine theta is x over r, and tangent theta is y over x. Correct? Now we will now define our sine, cosine, tangent if they are in coordinate system using these formulas here. Let me box it. You need to memorize this. Okay, you need to memorize that. Let's say suppose that's the definition, right? Now the thing is, once I use that kind of definition, then I can actually go to notice. Maybe I go on this way first. Notice that this new definition is consistent to our right triangle definition, the one we did yesterday. So what I'm saying is this, we have a new definition right now, but it's not that we are replacing it, we are actually extending it. The definition we have yesterday applies only for right triangles. Right now, you will see that we don't need a right triangle. We actually don't need a right triangle. You can pick any point on the coordinate system. Let's say this is my point. Let's say my point here is -5, 12. Okay, -5, 12. Then the associated angle will be this guy here. Let's say this is theta. Okay, now if that's -5, so the length here is 5. The length here is 5. Okay, and the y is 12. Then the hypotenuse will be 13 by Pythagorean triple. Okay, now then using that idea, what will our sine theta be? Sine theta will be y over r. Cosine theta will be -5 over x over r, but the x is negative now. While tangent theta will be y over x. That will be 12 over r. Okay. Now, from here we can see that. From here we can see the following. From here we can see the following that. Oops. In quadrant 1, all signs, sine, cosine, and tangent are positive. In quadrant 2, the y is positive, but the x is negative. So in quadrant 2, you will see only sine is positive, yet cosine and tangent are negative. In quadrant 3, maybe I write the coordinate. The coordinate will be negative, negative, right? In quadrant 3, then the sign will be y over r. Notice that the r, the hypotenuse, is always positive, right? So the sine and cosine will be negative. The tangent will be negative over negative, which is positive. And finally, in quadrant 4, the coordinates is the x is positive, the y is negative. So you see that the sine is negative. Actually, sine and tangent will be negative. Sine and tangent will be negative. And cosine will be positive. Now, I suggest you to memorize it this way. Memorize the positive. In quadrant 1, all's positive. In quadrant 2, only sine positive. In quadrant 3, only tangent positive. In quadrant 4, only cosine positive. All sine, tan, cos. ASTC. Up to you how you want to memorize it. Yeah, up to you how you want to memorize it. Okay. Suppose, for example, I pick question number 76. Number 76. P, the coordinate P is -8, -15. So I sketch that -8, -15. This is my P here, -8, -15. So the hypotenuse will be 17, right? So the angle will be this angle. This is the angle theta. According to our definition, what is sine theta? That will be y, -15 over r, 17. Cosine theta will be dx, which is -8 over 17. And tangent theta will be -15 over -8, which becomes positive 15 over 8. Okay. Now that's for 5.2. There's more things I would like to do there. Oh, you know what? Yesterday we did computation for trig functions. I need to go over this again. Number 30, we did computation for trig functions in degrees. Number 30, for example, let me go over that. Part A, what is tangent 282 degrees? Then let me grab my calculator. I know you have scientific calculator. What you need to pay attention on is the mode. The mode needs to be in degree in this case, or radian later on. Let me check my mode. My mode already in degree. Okay, you see this one here? Yeah, it's already in degree. Now then, tangent to 82 degrees is -4.7 something. -4.70463. 0463. Remember, always 5 decimal places. 5 decimal places. Now, that's for part A. Part B, how about cotangent? -81 degrees. Now the thing is, we don't have cotangent function on our calculator. No, there's no calculator with cotangent function. No, there's none of them. But we can do the following. We know that cotangent is the reciprocal of tangent. So this is 1 over tangent negative 81 degrees. Okay. Then from there you use your calculator. I will do 1 divided by tangent negative. Now negative sign, you don't use subtraction sign on calculator, you use negative sign. Negative 81, the mode already in degrees. So that's negative 0.15838. Negative 0.15838. Okay, so don't forget that yesterday I only taught you to use sine or cosine tangent, right? But what happens if we have cotangent? Now you need to compute that as the reciprocal of tangent. Likewise for part C, we have secant 202. Secant 202 degrees. Secant is the reciprocal of cosine. So that's what you write first. Then from there, you plug into your calculator. It's already in degree mode, right? So keep in mind, when you use your calculator, okay, make sure that the mode is in line to the numbers you want to put in. This is 1 divided by cosine 202 degrees. That's negative 1.0785. 853. Okay, now then part D, that's easy, that's sine. So sine 97 degrees equals to, just use calculator right away, sine 97 degrees is 0.99255. 0.99255. Okay, now that's number 30. All the angles are already in degrees. I just need to be aware that what happens if the trig function we are dealing with is not the primary trig function. If it's not sine, cosine, tangent, then you need to rewrite it first, okay, in terms of sine, cosine, tangent, then do the reciprocal first, and then you use your calculator. Number 32, part A, this is sine negative 0.11. There's no degree sign. So it must be in radian. Go to your calculator, change the mode. Go to the mode. On my calculator, I go to this mode here and go to radian. Okay, now then I put sine negative 0.11. That is negative 0.10978, so 978. Okay, let me warn you ahead that if I use degree there, sine negative 0.11 degree, the value will be different. Go to degree. Sine negative 0.11. You see that it gives you different value, but that's because different mode. Okay, that's because different mode. That's negative 0.0019. Now part B. What is secant 2 pi over 5? Secant 2 pi over 5. This is equal to 1 over cosine of 2 pi over 5. Then we use our calculator. This is 1 divided by cosine of 2 pi over 5. That's 1.001.00024. Okay, that's for part B. Part C, how about tangent of -3 over 13? Tangent of -3 over 13, that's straightforward. Tangent, oh, I need to change. Oh, hold on. Did I change the mode here? Oh, it's still in degree. I'm sorry. So earlier the answer was incorrect. The answer was incorrect earlier. So no, this is not right. This is not right. This is not right. Okay. So that's 1 over cosine 2 pi over 5. It's 3.2 something. 3.23607. 3.23607. Okay, you see the difference, right? I didn't check the mode, right? I just go ahead right away and I make a mistake that I don't realize. Yeah, I did a mistake that I don't realize. I honestly don't remember earlier what makes me realize that. In other words, if you don't make it as a habit that always check the mode, deal with the mode, right? There's no way for you, if you unless it becomes a habit, there's no way for you to actually figure out that you already make a mistake with your calculator. Okay, now tangent -3, tangent -3 over 13. That's already in gradient, right? Okay, that's -0.23495. -0.23495. And finally, part D about cosine 2.4 pi. Cosine 2.4 pi. That's cosine 2.4 times pi. That's 0.30902. 0.30902. Okay. Now, suggested homework from 5.1. I wonder if I give you the suggested homework from 5.1. Didn't. Huh? The suggested homework from 5.1 from number 1 to number 37. And then I would like you to go on with number 43, 45, 47, and 51. That's for 5.1. Now 5.2, yesterday I believe I gave you some suggested homework. So yesterday I gave you some suggested homework. Okay, continue from there. But on the top of that, I need you to do number 75, suggested homework. 5.2b, number 75 and 77, number 87. We will continue with 5.2 after the break. Okay, right now it's 12:10. We come back at 12:20. We are still in 5.2. We are still in 5.2. Let's take a look on some problems that we could actually done it, but it does take some insight to disassemble the information. Number 90, for example. Number 90, we have cotangent theta equals to 3/4, and cosine theta is negative. Now, the first thing we need to do is we need to figure out which quadrant is this. What quadrant is this located? Now, if cotangent is positive, that's positive, right? Okay. Then tangent will also be positive. In fact, the tangent will be 4/3, right? That will be also positive. Now, which quadrant is which quadrant has tangent is positive but cosine is negative? Because cotangent theta is positive while cosine theta is negative, then theta must be in quadrant. And you kind of like remember what we have here. The quadrant where the cotangent, therefore tangent, is positive, yet the cosine is negative. That's quadrant 3. Okay, so now then you kind of like disassemble that cotangent theta equals to 3/4. Okay, so if you have a theta, okay, in quadrant 3, okay, now remember tangent is y/x, right? Okay, so you need to have the ratio to be 4/3. But we know in quadrant 3, the x and the y are both negatives. So this must be -4 here, and this must be -3 here. Think about it. We can say tangent theta, which is 4/3, now can be seen as -4/3 because it has to be in quadrant 3, right? Because it has to be in quadrant 3. The x and the y has to be negative. So you kind of like rebuild it that way. Okay, oh, then if that's the case, we will have our hypotenuse, or the r will be 5. Okay, so we can assign, okay, let's assign the y to be -4, the x to be -3. Then from there we can go on what is sine, what is cosine. Sine theta will be the y/r. Cosine theta will be the x/r. Tangent theta we already have it, cotangent theta already have it, secant is reciprocal of cosine, sine is reciprocal of cosecant. But the key is really in dissecting it, okay? Kind of like do the trick where you separate the x and the y, okay? Let's do another one, let's say we do number 94. Number 94, cosecant theta is 5, while cotangent theta is negative. Cosecant theta is 5 means the reciprocal implies the reciprocal is sine, right? Sine theta is +1/5. Cotangent theta is negative implies tangent theta, the reciprocal, is also negative. Sine positive, tangent negative, so theta is in quadrant 2. Now, once you know it is in quadrant 2, then let's work it out. Sine theta is 1/5 y over r, right? Sine theta equals to 1 over 5. That's y over r. Okay, so the y is 1, the r is 5. How about that? And how about the x? Then use Pythagorean Theorem. Okay, x squared plus y squared equals to r squared. But don't forget, because it's in quadrant 2, the x later on will be negative. Okay, so x squared plus 1 squared equals to 5 squared. Fast forward, x squared equals to 24. X equals to plus minus square root of 24. But x is negative. Notice that theta is in quadrant 2. Okay, so x equals to the negative branch of 2 square root of 6. Now then, from there we can go on. We already have the sine. How about the cosine theta? Cosine theta will be negative 2 radical 6 over 5. Tangent theta will be y over x. Rationalize a little bit, I get negative radical 6 over 2 times 6. Once we get the sine, cosine, and tangent, then we also know the cosecant, secant, and cotangent. Okay. Together with that, we can go on further. Earlier, I asked you to do number 87. You can go further to do number 96. You can go on further doing number 96. Okay. Now, I will separate. There's the third part of 5.2, which I don't think I want to do right now. Right? I have something more urgent I need to teach you, and I will go to the identities, I guess, tomorrow. Should I do that today with our textbook, the way our textbook does it? Yeah, let me go on to 5.3 first. To be honest with you, our textbook here is designed in the way that they assume you have some trigonometry, and therefore they kind of like do the foundational part really fast. But I know that there's a big chance that you actually don't. So I want to put the foundation, numerical foundation first, and a strong feeling on how the trig functions actually works. And then we go on to the proofing thing. Okay. Yeah. Now 5.3a. So I owe you. We are done with 5.1. Okay. I leave the proofing part, the identity part, in 5.2 until tomorrow. Okay, so I will call that 5.2b. Okay, and even this 5.3, it will take some while That's not something we can finish right away today, but I will try to build your intuition a lot more. Okay, now what is 5.3b? We will start with an even newer definition of trig function. Even newer definition of trig functions. From the definition we have earlier, in 5.1, as I remember, or 5.2, we have this. We have a unit. We have a circle. Okay, and then I suppose superimpose that on coordinate system. Okay, and then we say that if I have a point on the circle with radius r, if I have a point on the circle with radius r, let's say that coordinate is coordinate p, x, comma, y, this is r here, then we define sine theta in standard position. Sine theta equals to y over r, cosine theta equals to x over r, and tangent theta equals to y over x. Right, now that's what we learned before. This is in 5.1, as I remember. No, that's 5.2. From 5.2. Now, the third definition here gives us another approach in teaching trigonometry called unit circle approach. So the one I started with was right triangle approach. Okay, there's another approach called unit circle approach. Now the thing is, once you are in pre-calculus and on, you should know both approaches. Okay, so what I'm doing now, yesterday I introduced you with right triangle approach. Right now I try to relate that to unit circle, and unit circle approach is actually a lot more excellent in solving equations, as you will see much later. For now, don't worry about it. I just try to show to you that with the definition we had earlier, if we go on a bit further, okay, the earlier means if you have a circle with radius r and p, coordinate p is on the circle, then the trig functions is given by this, right? Now imagine, consider unit circle. The unit circle. Now we call a unit circle if the center is origin and the radius is 1. Now, that's where the key step happens. What will happen then? Well, then we will have a unit circle. The radius is 1. Right? The radius is 1. Okay. Such that if I have a point on the circle, if I have a point on the circle, let's say this is theta here. Let's say this is theta here. Okay, the radius is 1, right? And let's say this coordinate is coordinate xy. Remember, it's a unit circle. Remember, that's a unit circle. Then, by definition, sine theta will be y over r, but the r is 1. And cosine theta is x over r, but the r is 1. So we can now replace x comma y, which is a coordinate on the circle, right? Let me write it down. Let p x y be a coordinate. Earlier in 5.2, I said that px is a coordinate on that circle. Right now, it is a coordinate on a unit circle. Because it is unit circle, then the radius is 1. Okay, now, but the consequence is, now I can write x as cosine theta, the y as sine theta. Okay, so now I can write this as the x component is cosine theta, the y component is sine theta, as long as the radius is 1. As long as the radius is 1. Let me ask you to absorb that a little bit. Let me ask you to absorb that a little bit. As if I'm saying the following. As if I'm saying the following. Suppose, for example, let theta be in quadrant 2 and sine theta equals to, let's say it is 0.3. Now we know in quadrant 2, sine is positive, right? In quadrant 2, sine is positive. So find cosine theta. Now, I don't want to get you too much into formula, but I need you to learn it visually for now. Okay, at least do it that way first. Okay, so imagine you have a unit circle. Imagine you have a unit circle. And then the sine theta is 0.3. So suppose it's in quadrant 2. So let me just pull a point on that circle in quadrant 2. And the sine is 0.3. But sine in unit circle gives us the y. Now the question is, what is the cosine? What's the cosine? And we can apply Pythagorean theorem here. Okay, just find the x, and whatever that x, that will be your cosine theta. Okay, so solution. You see that x squared plus y squared equals to 1. That's a unit circle, right? Okay, but we know the y is 0.3. Okay, so 0.3 squared, 0.09. So x squared is 1 minus 0.09. That's x squared equals to 0.91. So x is plus minus square root of 0.91. Now then we know that theta is in quadrant 2. So x should be negative. So x is negative square root of 0.91. But we also know that x here will be the cosine theta. So cosine theta equals to negative square root of 0.91. And from there you use your calculator. I get negative 0.95394. Now notice that we don't have that privilege. We don't have the privilege of saying sine theta equals to y if that's not a unit circle. Okay, if they give you a coordinate 3, 4, for example, that's definitely not unit circle. Okay, that's definitely not, because the radius is not 1. But you still, like, if they give you 3, 4, for example, you can find the radius is 5, right? And then the sine will be 4/5, for example. But here they don't tell us the radius, they just tell us the sine. Then just put that sine theta as a y on the unit circle right away. Okay, so you see that in 5.1 or 5.2, we have a question very similar to that. This one here, number 94. Yeah. See 94, or maybe the one before that. Oh, both of them tangent, cotangent. Yeah, both of them tangent, cotangent. No, not doable. Is there anything else? Let me go back to 5.3. Suppose I say this thing. Alternatively, using method 5.2. Theta is in quadrant 2 and sine theta equals to 0.3. Now I will rewrite this as 3/10. Okay, and then so I don't look at that as from the unit circle point of view. I just see that as a coordinate where the y is 3, the hypotenuse is 10. Okay, so what's the x? Solution: x squared plus y squared equals to r squared, right? This time I say the r is 10, the y is 3, I need to find the x, right? So x squared plus 9 equals to 100, so x squared equals to 91. X will be plus minus square root of 91. But here, x is not the cosine though. No, it's not, because it's not unit circle. The radius is not 1. Okay, but since theta is in quadrant 2, then dx is negative. So x equals to negative square root of 91. Now, what is cosine theta then? Cosine theta will be x over r. That's negative square root of 91/10, which if you compute, you will get the same value. So it will be negative 0.95394. Okay. So we have actually two methods to do that. We actually have two methods to do that. So if we have sine, cosine, and you need to solve given one, you need to get the other, then you can use this method. Now, of course, once you get the sine and cosine, you will be able to find the tangent, right? Yeah, you will be able to find the tangent. Because tangent, as you have seen, that's basically y over x, that's sine over cosine. Now, but there's one big benefit of using this unit circle. Things that we could not do before, now we can do. Going back to the unit circle, going back to unit circle. Going back to unit circle, let me make it big enough this time. Now you remember that the angle theta, let's say this is theta, okay, then the coordinate here will be cosine theta, sine theta, right? Okay. If we know the angle, then the coordinate is the x component of the coordinate is the cosine of that theta. The y component of that coordinate is the sine theta. Now, with that said, let me go here. What happened at this point? What is the coordinate here? If this is unit circle, the coordinate here is 0, 1, right? Okay, but this coordinate here corresponds to theta 90 degree, right? Okay, so using the idea we have earlier, this is actually cosine 90 degrees, comma, sine 90 degrees. Is it right? So we have new special angles. Sine 90 degrees is 1. Cosine 90 degrees is 0. Okay, in fact, we can go further. Tangent 90 degrees is y over x, which is undefined. Okay, and furthermore, let's say we look at this coordinate here, 1, 0. The associated angle is 0 degrees, right? So this is cosine 0 degrees, sine 0 degrees. Then we see sine 0 degrees is 0, right? That's the y component. And cosine 0 degree is 1, and tangent 0 degree is the y over x, 0 over 1, that's 0. You see? So you can memorize that, right? And in fact, you should memorize that. You should memorize that. You should memorize that. Now, using the same idea, we can develop it this way. Imagine this coordinate here. The associated angle is 180 degrees. Right? Okay, that's the associated angle. So from there, we can get the coordinate here is -1, 0, right? That's -1, 0. So from there, we see sine 180 degrees is the y component. Cosine 180 degrees is the x component. And tangent 180 degrees is the y over x. sorry, it's -1 for the cosine. That's it. Okay. I don't think there's any other way to come up with this cosine, sine, tangent, 180 degrees, 0 degrees, 90 degrees, except by doing what I have done here. Okay, except by doing what I have done here. Going further, okay, use this. This is 270 degrees. The coordinate here is, the coordinate there is 0, -1. So we can see that sine 270 degrees is -1. Cosine 270 degrees is 0. Tangent 270 degrees is -1/0. That is undefined. That's another thing you have to memorize. Okay? That's another thing you have to memorize. Then you will see the following pattern. Let me grab it from my notes. We will summarize this further. We will summarize this further later on, but let me get it from, let's see, to summarize all those pictures. To summarize all those situations, I will show you a unit circle. This unit circle. Suppose I have this unit circle. For the next couple minutes before we take our break, we will do the angles in radian and degrees, and then the coordinates for those special angles that we already know. Okay, for example, we have known that this is 0 degrees, this is 30 degrees, 45 degrees, 60 degrees, 90 degrees. Okay, if I go further, this is 180 degrees, 270 degrees, and going back here, 360 degrees. Okay. We can say right now this is the special angles that you should have memorized. How about the radian? We know 0 degrees is 0 radian. Okay, 180 degrees is pi radian. 90 degrees is pi over 2. 45 degrees is pi over 4. 30 degrees is pi over 6. 60 degrees is pi over 3. Okay, so this guy here will be 3 pi over 2. And of course, this is 2 pi radian. Just now, we did the coordinates for 0, 90, 180, 270 degrees. The coordinates for 0 degrees is 0, 1, 0. Therefore, from here we know that cosine 0 degrees is 1, sine 0 degrees is 0. Okay? Yeah. But once you know the coordinates in the units on the unit circle, then you know the value of the sine and cosine associated to the angle for that point. This is 0, 1, which means cosine 90 degrees, the x component is 0. The y component, sine 90 degrees, is 1. This guy here is -1, 0. This is 0, -1. Now, how about when the angle is 30 degrees? Or when angle is 30 degrees, then the coordinate is supposed to be cosine 30 degrees, sine 30 degrees. Is it right? Supposed to be. But what is sine 30 degrees? That's 1/2. Cosine 30 degrees is radical 3/2. For 45 degrees, that's sine 45 degrees. I'm sorry, the first component is cosine. Cosine 45 degrees, sine 45 degrees. Could be confusing. We know sine 45 degrees, you should memorize from yesterday. Radical 2/2 for the cos, for the sine and also for the cosine. For the 60 degrees one, that's cosine 60 degrees, sine 60 degrees. Cosine 60 degrees, we know it was 1/2, and sine 60 degrees, radical 3/2. Now, one thing I suggest you to do later on, I will post this handout on our discussion board so that you can print it out and then try to fill it up. Okay, it trains you with multiple aspects and visualizing them at the same time. So far, we only did the first quadrant and those what's that, quadrantal angles, like the one on the positive negative x-axis and positive negative y-axis. Now, after this, maybe I think tomorrow, later we will extend this to quadrant 2, quadrant 3, and quadrant 4. We'll extend this to quadrant 2, quadrant 3, and quadrant 4. Okay, but let's take a break first. We come back at 12:58. 1:10, let's say. We come back at 1:10. Okay, let's start again. I will repeat what I did just now on that unit circle. Okay, but I will repeat it, but then I will focus and then I will extend it. Okay, I will repeat it, but I will also extend it. This time I will make it big. This time I will make it big. I hope this is big enough. Okay. Now, this is 0 degrees, 90 degrees, 180 degrees, 270 degrees, 360 degrees. So you see 360 degrees, you go back to the same coordinate at 0 degrees. The radian, this will be 0 radian, pi/2 radian, pi radian, 3 pi over 2 radian. This is 2 pi. The coordinate, this is 1, 0. This is 0, 1. This is -1, 0. Remember the x, y represent the cosine then sine respectively. And this will be 0, -1. Okay, then we have 30 degrees, 45 degrees, 60 degrees, 10 degree sign there. And the corresponding angles in radian will be pi over 6, pi over 4, pi over 3. The coordinates for 30 degree cosine 30 degrees is radical 3 over 2. So when you do this exercise at the same time, it makes you, forces you to memorize the value of sine, cosine of 30, 45, 60 degrees. This is radical 2 over 2. That's cosine 45 degrees, sine 45 degrees, radical 2 over 2. Cosine 6 degree is 1/2. And sine 60 degree is radical 3 over 2. Now, that one is easy. That one is easy. Now, what happened with the special angles in quadrant 2? Special angles in quadrant 2. Now, the special angles in quadrant 2 has the following behavior. That this is a special angle. This angle here is a special angle in which the angle to the negative x-axis is 30 degrees. So you see this is 30 degrees here, right? Okay, that one is 30 degrees there. Okay, now this is 45 degrees here. This is 45 degrees, has something to do with this. And the 60 degrees here has something to do with this. And you can see from the picture that the coordinates on the left-hand side with those angles is basically the reflection of that coordinate with respect to the y-axis. 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 So now imagine if, for example, imagine if we have this angle here. What is this angle? Now this is 180 minus 30 degrees, right? Okay, can you imagine what's that? That's 150 degrees, right? That's 150 degrees. The radian will be pi minus pi over 6. That's 5 pi over 6. Now, how about the coordinates? The coordinate will be the opposite of x, negative radical 3 over 2, comma, the same y, 1/2. See, the x is opposite, right? The x is opposite. The x is opposite. The x is opposite, the y is the same. Okay, so I want you to compare this guy with that guy. They're opposite. Okay. Now you will see this guy here corresponds to the guy there. the same y, but opposite x. Opposite x, negative radical 2 over 2, and the y stay the same, because the same height. That's why I strongly suggest you to memorize what you have on this side first. Okay, if you memorize what you have on that side, then developing that into quadrant 2 or quadrant 3 will be a lot easier. Okay. Now, how about this guy here? This guy here will correspond to the guy here. The x will be the opposite, negative 1/2. But the y will be the same, square root of 3 over 2. Okay, now how about the angles? The angles, 45 degree from 180, that's 135 degrees. The radian will be 3 pi over 4. 60 degree from 180 is 120 degrees. That's pi of 3 less than pi. That's 2 pi over 3. You need to memorize this. Okay. Now do not memorize it as if when I ask you sine 120, what's that? No, not now, not now. Eventually you will. I think within 2 or 3 days you should. Okay, within 2 or 3 days you should. But we have this way, I try to put this into your visual memory first. For example, 120 degree corresponds to 60 degrees. Okay, 120 degrees correspond to 60 degrees. Therefore, the value of x and y must be the same except the plus minus. Okay, there's one term that you will see in future called reference angle, but let me tell you now what's that. Reference angle is the following. Like for example, 45 degrees has reference angle 45 degrees. This is the reference angle. Now, 45 degrees has the same reference angle with 135 degrees. That's the same reference angle. Now, if two angles have the same reference angle, then the coordinate will be the same except the plus minus sign. Let me say it again. Reference angle the same means the coordinate the same except the plus minus sign. Now, what is reference angle to start with? The reference angle of angle theta. So angle theta is in standard position. Now reference angle denoted by theta hat is the acute angle is the acute angle formed by the terminal side and x-axis. Notice that I didn't say positive x-axis. I just say x-axis. Okay, so for example, this angle here, this terminal side here, the angle in standard position is this. This is the angle in standard position. But the reference angle is this. This is the reference angle. Okay, that's the reference angle. Now, if I pick, for example, I pick this one. Let's say I pick this one. Then this is the angle in standard position. This is the reference angle. So reference angle is the acute angle. It must be between 0 to 90 degrees from x-axis, regardless positive or negative x-axis, to that side. Okay. Let's do one more, just visually, to help us visually, to visualize that. Let's say we talk about this side here, this side here. Now the angle in standard position is this guy. This is the angle in standard position. However, the reference angle is this. That's the reference angle. Okay, now you will see, at least from what we had earlier up here, you will see that if the reference angle is the same, like this guy has reference angle 30 degrees, this also have reference angle 30 degrees. Oh, it's hard to see, huh? Then the coordinates must be the same, except that the coordinates must be the same, except the plus minus. Okay, you see that this reference angle here, this angle has the same reference angle with this, so the coordinate must be the same, except the plus minus. Now, developing that into quadrant 3 and quadrant 4, let's do to quadrant 4 first. So 30 degrees in quadrant 4, reference angle 30 degrees in quadrant 4 is this angle, right? Okay, is that angle. So the coordinate, let me use blue. Okay, then this will be 330 degrees, 360 minus 30, right? Okay, the radian will be 11 pi over 6. Now, how about the coordinate? You will see that the coordinate here and the coordinate here should have the same coordinate except the plus minus sign. You see that the x will be the same, right? The x will be the same, the y will be the opposite. So this will be radical 3 over 2, the same x, but the y is negative 1/2. Negative 1/2. Okay. Likewise, the coordinate in quadrant 4 that has reference angle 45 degrees is this guy. Okay, so 45 degrees minus, subtracted from 360 degrees is 315 degrees. The radian is 7 pi over 4. So how about the coordinate? Now the coordinate must have something to do with that coordinate up there. Must be the same numbers except the plus minus sign, because they have the same reference angle. Now, what is the coordinate? You can see the same x, right? But you reflect with respect to x-axis, so the y will get the opposite. Okay. Now, eventually you will see that the blue one, for example, the blue one, this guy corresponds to, this guy has the same reference angle with this, right? The same reference angle with that, the same reference angle with this, the same reference angle with this, the same reference angle with this. So you see that it creates a box, right? Now everybody in that box must have the same coordinate except the plus minus sign. So this will be negative radical 2 over 2, negative radical 2 over 2. The angle is 225 degrees, 5 5 pi over 4 in radian. How about the yellow one? This guy here will have the same reference angle with this. Not the same standard angle in standard position, no. The angles are not the same. The angle in standard position are not the same. But the reference angle are the same. So they must have the same coordinates. Okay, except the plus minus sign. Now, how do we figure out the plus minus sign? Then imagine the position in quadrant 1 or 2 or 3 or 4. Okay. With that said, then you can see if I go on with this here, it must have the same reference angle with this. You see, if you don't follow me in drawing this since the beginning, you will get super confused with so many informations put together. But at the same time, you did tell me, I overheard you say that in your heart, Thomas, I am an audiovisual person, right? You're audiovisual, I give you audiovisual. I give you a graph, but this graph can be so complicated such that this graph can be, as you can see here, it gets so complicated such that, you know, you still need to follow me from the beginning. Okay, you're telling me, oh, Thomas, I'm a audiovisual person, doesn't cut it. No, because I give you audiovisual, I give you picture. You still need to follow it. You still need to memorize it. You still need to actually follow how I get all these numbers. Okay, now this is 60 degrees from 360. This is 300 degrees. This will be 5 pi over 3, and then the coordinates will be 1/2, the same x with the one in the first quadrant, but the y will be the opposite, negative radical 3 over 2. The one here will be negative 1/2, negative radical 3 over 2. The angle will be, this is 240 degrees. The angle will be 4 pi over 3 in radian. Oh, I'm missing this one. This is 210 degrees. With the radian will be 7 pi over 6. Wow, that's a lot of stuff, huh? That's a lot of stuff put together. Yeah, but yes, I need you to memorize this. I need you to memorize this. Let me give you a little break. I mean, take a little break, pause this video first, try to memorize this. And then if possible, try to copy this on the handout that you can print out. Okay, copy this on the handout. And basically stare on that, you know, and try to have some logic. You will see that you will need to memorize this part, especially you need to memorize the one here. You need to start from here. From there, then you can go to the second quadrant, the third quadrant, the fourth quadrant. Okay. That's for this unit circle and special angles. Unit circle and special angles. Of course, tomorrow we will find another way to memorize these trig values for special angles in other quadrants, in quadrant 2, in quadrant 3, in quadrant 4. We will learn tomorrow how to memorize the values. Okay, it's not a single step like this. Okay, right now I ask you to memorize that pictorially. Okay, and tomorrow we will see that algebraically. Now, some important properties. I actually shift to another. I don't finish this section yet. 5.3, I don't finish it. Okay, because 5.3 has something to do with graphing, which I will not do yet. But I will go on to some basic identities. I'm sorry. Okay, basic identities. There are a lot of formulas you need to memorize. Even these basic identities that I will do in the next 20 minutes here, there are 4 big groups. Okay, I need you to memorize this, let's say today. Okay, tomorrow we will apply them. Well, if you don't memorize it tomorrow, then the harder you will move forward. Okay, I know that's a lot of material today, a lot of material, but I try not to hit 5.1 all the way, 5.2 all the way, 5.3 all the way right away. Again, their point of view, this textbook point of view is that you have taken trigonometry class in the past, while the prerequisite for this class is only geometry. Okay, which means you have some very, very foundational trigonometry and how to use them, but never into the theoretical point of view. Okay, now then I need to not to hit them all hard. I kind of like do the easy part for 5.1, easy part of 5.2, easy part of 5.3, and then tomorrow I will go back to 5.2. Okay, in how to use these basic identities. Okay, and then I go back to 5.3 tomorrow in using these to graph. Okay, so tomorrow we will have the basic graph of sine and cosine function. And then on Thursday, we go on into the graphs of a more general graph. That's basically, we finish up 5.5, 5.6 Thursday. We basically finish chapter 5 on this Thursday. Okay, and at that time, we may have very likely gone to 6.1, maybe with 6.2. Okay, so basically this, at the end of this week, supposed to be done with chapter 5 for sure. Very likely we already reached 6.2. Okay, I'm sorry, it's fast, And by the time of the end of next week, we should be done with 7.2. Okay, so within a couple of days, let's say in 3 days, we finish 1 chapter. Okay, this section here supposed to be something we can finish in 3 days, but knowing your foundation is not from trigonometry background, then I try to slow down. But this is summer class, so you also need to go fast. Okay, now here, go back, basic properties. This part is so important that I set it aside. Basic properties, or maybe to be more precise, basic identities. That's the right word. Identities. There are 4 basic identities. The first one is ratio and reciprocal. Ratio and reciprocal identities. First one, tangent theta is equal to sine theta over cosine theta. Part B, secant theta is the reciprocal of cosine theta. Part C, cosecant theta is the reciprocal of sine theta. And finally, cotangent theta is the reciprocal of tangent theta. The last 3 are actually just definitions. Now, the first one, however, is not really from the definition. And we can see that this is true because of the following. Notice that sine theta over cosine theta is defined to be, let me use the one we have in unit circle. Sine theta is y, cosine theta is x, right? Using definition in unit circle. But at the same time, y over x, even in unit circle, is actually the definition of tangent theta. Okay, now even if you don't see that as a unit circle, the sine theta is y over r, cosine theta is y over r, this is equals to y over r times r over x, right? The reciprocal of x over r. And the r cancels, we get y over x, that's tangent theta. So you see, we have two different ways to actually show that this identity is true. Okay, now that's the first identity. You don't need that to, well, these identities, you're supposed to memorize it in this order. But for the first one, basic identity one here, we use it so often that we don't even remember which one comes first, which one comes later. Okay, but I would like you to memorize my identities, the one I give you. You may want to write it on the flash paper, flashcard. Okay, and then memorize it in that order, especially the second, the third, and the fourth group. The second group, you need to memorize it in this order now, from now on. Pythagorean identities. The first one, let me call that 1 instead of A. So the one I use numbers, you need to put you memorize it in order. Sine squared theta plus cosine squared of the same angle is equal to 1. Proof. Maybe I prove it later. Let me write it down first. The second one is tangent squared theta plus 1 equals to secant squared theta. The third one, 1 plus cotangent squared theta equals to cosecant squared theta. Some notation. When you see sine squared theta, that is actually the same to sine theta being squared. Okay, so the theta you put into the sine first, whatever the result, you square it. Then you will see that in general, this is not the same to sine of theta squared. Okay, different order operations. Okay, different order operations. Sine squared theta means you put the theta into sine first and then you square it. Sine theta square, you put the theta into the squared first and then you put it into sine. So different composition of function. Okay, now memorize these second basic identities in that order, and you will see, especially when we go to calculus 2, you will need these identities heavily. Okay, you need to, by that time, you need to memorize this by heart already. Okay, yeah. The situation is a lot worse there though. Okay, under no time, under no situation, you can pass calculus 2, not even the first 1 month of calculus 2 without knowing your trigonometry well. No way, no way. I taught calculus 2 many times. I can tell you this. No one passed calculus 2 if their trigonometry sucks. Okay, now proof. Proof for B who 1. I hope you understand my coding. B for the basic, 2 for the second group, Pythagorean identity. The first one is the first identity in that group. Okay, proof. We start with this. We know that sine squared theta plus cosine squared theta is equal to, depends on which point of view you like to use, but let me use, let p xy be a coordinate on a unit circle, or let's say a coordinate on a circle. It doesn't have to be unit. So you have a circle, right, coordinate system, okay, and then let's say our p is here. This is our p, x, y. Now, of course, then this will be the radius, right? This is the radius. Okay, now sine theta is y over r, cosine theta is x over r. So sine theta is y over r, that's sine theta, being squared, plus cosine squared theta is x over r being squared. Now, I hope now you see why we call this Pythagorean identity, because then it relies on the Pythagorean theorem. They already have LCD, y squared plus x squared is r squared, right? Which is equal to 1. So, sine squared theta plus cosine squared theta equals to 1. That's B21. Now you can prove B22, B23 similar way. Okay, so let me prove that here. Proof for B22. Okay, you can use the similar way, but let me do it slightly different ways this time. I will start from sine from B21. From B21 we have sine squared theta plus cosine squared theta equals to 1. Give me a second. Okay, now then, again, there are many ways to prove this second identity in this group. Okay, one of them is actually use the coordinate on circle. Okay, but the second method is you use the formula that we have proven. Okay, now that's the beauty of math, that instead of doing everything from scratch, you can use the formula or identities that we already validate earlier, and this time I will divide by sine squared theta. I will divide by sine squared theta. So the first term will become sine squared theta over sine squared theta. The second term is cosine squared theta over sine squared theta equals to 1 over sine squared theta. Okay, so I basically divide each term by sine squared theta, but you see the first term now becomes 1. The second term becomes, oops, no, this is B23. That will be cotangent squared theta, and this will be cosecant squared theta. That's B23. If for B22, you actually divide by cosine squared. For B22, you can use this technique using cosine squared. Okay, now that's for the second group. That's for the second group. The third group. The third group. Co-function identities. Co-function identities. Now, in these identities, we want to see the relation between a trig function and its co-function. So basically, what sine theta has to do with cosine. Tangent theta with cotangent. And secant theta with cosecant. Now, the identities are, first, let A and B be complementary angles. It means those two angles add up to 90 degrees. Okay, so then the first one, sine A equals to cosine B. If two angles are complementary angles, then they are related by co-function of trig functions. So sine and cosine. Okay, A and B are complementary. Okay, tangent and cotangent. A and B complementary. Secant, cosecant. A and B complementary. Okay, so literal example, suppose for example, what is sine 40 degrees equals to cosine 1? Then what number add up to 90? 40 plus what gives you 90? 90 minus 40 is 50. Right? Tangent, let's say 70 degrees will be equals to cotangent 20 degrees because they add up to 90 degrees. Okay, one of the phenomena that we have seen is this. So you know that sine 30 degrees is 1/2, right? And you also see cosine 60 degrees also 1/2. Do you realize that? Okay, such that we can actually put these functions, these identities, rewrite it in slightly different ways. We can write this in slightly different ways. What is that? We can write it this way. So sine theta is equal to cosine of the complementary angles, 90 degrees minus theta. Tangent theta equals to cotangent 90 degrees minus theta. And finally, secant theta is equals to cosecant 90 degrees minus theta. Okay, so either you memorize this one or this one, they are equivalent. Okay, they are equivalent. Basically, if two angles are complementary angles, then they are related by cofunctions. Now, how about the proof? I will give you a very simple proof. It's so a lot of visualization, you see. And implicitly, we have done this yesterday. Implicitly, we have done this yesterday. You see in this triangle, let's say this is A, B, C, right angle at C. Okay, so this is A, this is B, and this is C, right? Okay, now let me ask you to take a look on sine A. Sine A. What is sine A? Sine A is equal to A over C, right? Okay, but if you use B as a point of view, A over C refers to the adjacent of B over hypotenuse, right? This A over C is also the same to cosine B. Now, of course, A and B, capital A, capital B here has to be complementary for that to happen. Now, let's take a look on tangent. Tangent A will be A over B, right? But tangent A, which is A over B, from B's point of view, is actually cotangent. That's the reciprocal of tangent. From B point of view. So this is cotangent of B. And last one, how about secant A? Secant A is C over B. But C over B is also cosecant B. So the proof here is more about visualization. Okay, the proof here is more about visualization. Last part. I promise you this is the last one, but you need to memorize this. Group 4, negative angle. I need you to memorize this today so that tomorrow when we do the proving identity stuff, then we will have easier time. Okay, then we will have easier time in computing some angles also. The first one is, actually you just need to memorize 2, but why not 3? So sine negative theta equals to negative sine theta. Cosine negative theta equals to cosine theta, no negative. And the third one, tangent negative theta is negative tangent theta. We will need this tomorrow. How about the proof? How about the proof? By picture. By picture. Okay. Imagine you have a negative angle here. Let me do it this way. Negative angle. This is, let's call this angle negative theta. Now that negative theta, angle negative theta, is the same reference angle to theta, right? Remember that? It's the same reference angle to theta. Okay. which means the xy component must have the same value. The xy component must have the same value except the plus minus sign. In fact, you see from this picture, okay, the x component must be the same. So this is cosine theta sine theta. The coordinate here should be cosine negative theta sine negative theta, right? Okay, but from the picture, you see that the x component are the same. The x component are the same. So we conclude that cosine negative theta must be equal to cosine theta. The x component must be the same. The y component, as you can see from the picture, are opposites. Therefore, sine negative theta is equal to negative sine theta. By just looking at the graph, Now, then how about the tangent part? Well, tangent negative theta equals to sine negative theta over cosine negative theta, and then we use that property that we have learned earlier. Cosine negative theta is negative sine theta. Cosine negative theta is just cosine theta. You can take off the negative for free, but this is negative tangent theta. Okay. Then the reason I show you the proof, not only because I want to prepare you for proofing. In fact, tomorrow we'll learn proofing, more formal way. Okay, but the proof here, it's more into why the formula is true, why the identity is true. Okay, but for you, you need to memorize these 4 basic identities for tomorrow. The first one, ratio and reciprocal. Second, Pythagorean identities. The third one is cofunction identities. And the last one is negative angle identity. Okay, is there any suggested homework for you to study from 5.3? There are some suggested homework for 5.3. A. You can do number 1 to number 1 and then number 3. I think that's what we do for now. Not that much though. Yeah, not that much. Okay. So tomorrow I will go back to 5.2, doing the identities, and then go to 5.3, some verifying identities and computing angles. Okay, and then go on to 5.4. Even though it feels a lot heavy, but you will see tomorrow we can breeze through 5.4 actually quite fast, because what we have done here will be seen more formally by our textbook tomorrow. Okay, then see you then tomorrow.